Okay, so we have iron, and not all iron is magnetic. You know, plenty of iron that does not stick to your fridge or stick to other things. Iron can, though, easily be magnetized, so if you bring a magnet near iron, it becomes magnetic. But other metals that become magnetic are iron, nickel, cobalt, and potentially aluminum. Magnetism is related to a property known as electron spin, which is something we're not going to get into. That's left for quantum physics. Um, and if it lines up, it's called these magnetic domains. If they're in a line, we get a bar magnet or a permanent magnet. These ones here in this piece are unmagnetized iron. They're kind of all going in random directions. If I bring a magnet near that, the magnet will cause them to align, looking like strongly magnetized iron here, where they're all going the same direction, south to north. Partially magnetized iron here. They're at least all going in general the same direction. This is going to be a kind of weak magnet. Unmagnetized has stuff going this way and this way and this way. There's another one down and this way and that way and all kinds of directions. Okay. And yes, we learned the other day that if you break a magnet in half, it will form new poles. It will not be as strong of magnet, but it will form two magnets with new poles. And magnets we know form a magnetic field. The direction, I believe, goes from south to north. Every piece of iron, though, can become magnetized. So when electric current flows through a field or through a wire, it generates a magnetic field. Okay? This is a very, very important property, and this is why, or a portion of the reason why it's called electromagnetism. Magnets also can generate electric fields, but the compass needles will line up with the direction of the magnetic field. To use a magnetic field, you take your finger, your thumb, it has to be the right hand. We're going to use the right hand rule. Okay, it's always the right hand rule. You take your thumb, you point it in the direction of the current. The direction of the magnetic field curls around your direction of your fingers. So if you're looking at this one, if I want to know the direction of current, I see the magnetic field going there. I can put my fingers of my right hand along it. My thumb would point in direction of current. And you can do that either way. You can use either one. But we get these. The compass will also point in that direction. The magnetic field goes south to north. And yes, you can quantify magnetic field. Its value is B. We're not going to be doing the calculations with it in this class. We're just going to do the concepts with magnetic field. We did the calculations with electricity. If you go a loop, it keeps going around each time in that direction. So we can see here magnetic fields kind of around several current carrying wires. The single one being the most obvious where it's a spiral. Um, when you get this loop, it looks a little interesting, or multiple loops. With multiple loops like this, the strongest magnetic field is where there's multiple of them interacting together. Yes, magnetic fields don't generally cancel each other out, they more combine. So, most of you probably know about an electromagnet. Essentially, usually what you do is you take a piece of iron. Let's see if I can write sideways. Iron, usually because it's the cheapest of the metals that can be done with. And then I'm going to use blue to represent the wire. And I put a bunch of wires around this. The wires, when I pass current through them, when there's no current going through the wires, so let's say it's connected to a switch here. When the switch is open, we'll use a battery. When the switch is open, we have no current, it's not a magnet. When the switch becomes closed, current starts passing through and it produces a magnetic field. That magnetic field magnetizes the iron. This iron suddenly is a strong magnet, depending on the number of coils and the voltage and things, but can become a very strong magnet and pick things up. They'll sometimes use this to like pick up old cars and move them around. And as soon as you take the current off, you can have a not magnet and it just releases. So the problem that happens sometimes with strong permanent magnets where they just get stuck together or they get pulled together so strongly they can become dangerous kind of goes away because we have this ability to turn it on and off by shutting on and off the electric current. Um, this example over here, the maglev train is literally using electromagnets. I'm kind of assuming there's some permanent magnets here too, but if you're using a magnetic repulsion, two magnetic fields, they need to be strong enough to hold the one train up. So strong enough to equalize the force of gravity. And this is probably an electromagnet. No, maybe they put permanent magnet in the tracks. I'm not sure which one is which, but some sort of magnet. And the magnetic repulsion has to be a repulsion. So the fields need to go in such a way that they repel each other. So when I've got a current carrying wire, it's going to be surrounded with this. I believe that's repulsive. I don't remember for sure which way they. No, they got to be going the same direction. Same direction should be repulsive. Opposites attract. Wait, no, south to south. So if I had two magnets south to south, they'd go opposite. So yes, opposite. Never mind. This one going this way. This one going this way. Okay. Maglev speeds for trains can be about half of aircraft, so you can go a couple hundred miles an hour with maglev trains relatively safely because of the lack of friction. So we've talked briefly about a superconductor. A superconductor conducts without um, without electrical resistance. And the problem with electrical resistance ends up being that electrical resistance uses up my electricity, and I need to keep supplying voltage to keep generating current. Well, if you have a superconductor, the current will flow without resistance. So once you get that current flowing through the wire, you can effectively, I got a battery here, gets the current flowing. With a superconductor, I can just get rid of the battery and the current will keep flowing and it will keep generating that electromagnet. Um, the problem is we don't have anything that superconducts anywhere near normal temperatures. Most of them are, I think the best ones are somewhere around negative 100 Celsius. So, as cold as the poles get, like colder than they normally are. So there are some and they can use them, but they have to spend a lot of money cooling them. Um, Electromagnets, I'll explain how they work in speakers and electric motors and other things, but they're used in a lot of things. So, magnetic force on a charged particle. So here we have a magnetic field that looks like moves north to south. I guess I had that backwards. Magnetic field goes north to south. Oh, when it's outside the magnet. Okay. They're showing the domains going through the magnet going south to north. And then it continues outside going north to south. That's why. So this goes north to south. The current on it that's going, you can see in the picture, that is going left to right. So I put my thumb in the direction left to right. The current is going this way. We see that that is opposite the direction of the magnetic field. So it is going to repel it, pushing it away. Or you can use the right hand rule. This shows it sometimes better. Right hand along this, you put your fingers along this, curl towards the beam, then your thumb points in the direction of the force. So right hand along there, curl towards beam, forces up. If I either flip the magnet around, or if I flip the direction so that it was coming instead of the direction the book shows, if it were coming in this way, I'd have to take my hand. I can't bend my fingers backwards, so I bend them around forwards, put my hand along the magnetic field, but I can't bend them that way, so I have to put my hand over, bend it along, thumb points down, and that's going to show it on the next page, one with it going down. And here, so this first one was considered an electron beam, so it bends the beam. The second one is actually a physical wire, so it's bending the actual wire down. Look at the direction of the current, still aligned. I believe we have the magnets still the same. Yeah, this is. So they didn't show the poles on here, but they should have. North, south, north, south. So it actually physically bends the wire, doesn't just alter the beam as it goes through. So we've used some electric meters to measure electric current, and you can use it to measure voltage, and they kind of just convert each other. But an electric meter essentially has a magnet and a current carrying wire. This loop, when we run current through the loop, it changes the magnetic field. The strength of how long it changes the magnetic field moves this little magnet here. The magnet's connected to a spring that's going to generally return it to its original position. But it'll move as the magnetic field is generated in the wires. The stronger the voltage or the current, the more it moves. So that's how a analog meter, I believe we use some analog amp meters in the lab. That's how an analog meter works. Okay. Amp meters measure current or amperage. Volt meters measure voltage. Usually, most people use what's called a multimeter that can do both and can measure resistance and a few other things. Multimeters actually need a battery, though, not just a they need they need a battery, not just versus a straight ammeter or voltmeter can read it right off the circuit without any battery. Electric motors, and we'll come back to this in more detail after spring break. But the electric motor, or people watching this in the future in later lessons, electric motors essentially are using electromagnetism. Most of them use a permanent magnet surrounding a coil. Usually it's several coils of wire. And they're counting on this, the magnetic field, a series of attractions and repulsions. Well, the problem would be if this did not switch, it would not it would be attracted to one side and it gets stuck there. So it attracts and then it repels to keep it spinning. And yes, it does rely on having some momentum. And most modern electric motors actually have coils in 6 spots or 3 sets of coils to keep them from getting stuck. And they're connected to what these are. These stationary elements here are called contacts. The part that's touching it here is usually going to be known as brushes. Okay. The brushes connect the current. So every half loop, it's going to switch sides on this motor, which is going to then switch the direction. So it switches the magnetic field and keeps it rotating. Okay. Going to always have, so when this top one comes halfway around, it's going to switch so that it's, again, attracted to S's south pole as it's moving towards, attracted to south pole as it's moving towards, and repelled as it needs to move away. And between those two things, the brushes allow it to keep switching. Usually you have multiple, so it gets enough momentum to go past the point where it gets most strongly attracted. There's also something called brushless motors where they actually spin the magnet, and they now use computer switches to switch instead of brushes. Brushes do tend to wear out because they're rubbing and they're in contact, and most of them last quite a long time, but they wear out over time. So brushless motors don't have that problem because they're using a circuit board to do the switching of where the current is going through which one. They'll spin the magnet, and then they'll have coils like this, and like this, and like this, and they'll send the current through one coil at a time using electronic switching. Okay, that's the beginning of electric motors. We'll talk about them in more detail in chapter 25.